Welcome back. In the previous video, we have introduced a brief introduction about noise and nonlinearity in microwave circuits. And we have said that we have two types of noise. We have internal noise and external noise. Now we are going to discuss briefly what are the sources of this noise. So for the internal noise, the sources of the internal noise, it can be generated internally inside the device or the component, is usually caused by random motion of the charges or the charge carriers inside the device or the material of the device. This random motion is actually coming from different mechanisms. Uh, the most important mechanism is the thermal noise. Just heating up any material, it will cause the electrons or the charge carriers inside this material will move randomly inside this material, and this random motion will introduce random voltage or random current, and this random current will introduce random voltage, and this current and random voltage represent random noise. So the basic source for the internal noise is the thermal noise, which is caused by thermal vibration of bounded charges. Other types of internal noise is shot noise. This is due to the random fluctuations of charge carriers, and this is usually in the junction between two different types of semiconductor, between N and B, for example. We can find shot noise. Flicker noise, and flicker noise is varying inversely proportional to the frequency. So usually it is called 1 over F noise. And plasma noise. Plasma noise is introduced in free charge carriers, like ionized gases, for example, in vacuum tubes and so on. So plasma noise is random motion of charges in ionized gases. And finally, quantum noise, and usually quantum noise is much less than all of these types of noise, so it is usually neglected with respect to the other types. It is often insignificant relative to the other noise sources. This is coming effectively from the quantum effect of the particles to move from one atom to another atom with the uncertainty of the presence of the particle in somewhere. This will introduce some sort of noise, but usually this value is very small. On the other hand, sources for external noise, it can be introduced by receiving antenna or by electromagnetic coupling in some sort. For example, a very simple example for electromagnetic coupling is the cooling holes inside a microwave receiver, for example. You can find that there are some holes or slots in the package of the microwave receiver. These slots actually act as slot antennas, and they couple some power from the external to inside the circuit itself. And effectively, the problem of electromagnetic coupling or external noise is a very important point of engineering, and it has a complete science. It is called electromagnetic compatibility. So if I have, for example, a microwave device or RF device, it is required that this device should be compatible with other devices such that the radiated power from other device will not be coupled to the required device, and at the same time the required device will not radiate power to the other device, which will make external noise. So the details of the external noise, it will be discussed in electromagnetic compatibility, but briefly now we say that the sources for RF, for external RF noise, thermal noise from the ground. The ground itself has thermal noise, and this thermal noise is radiated around us, and any microwave receiver or any RF circuit will capture some power of this thermal noise from this ground. Cosmic background noise from the sky. Even the sky itself will introduce some noise, and this noise is radiating in random frequencies and in random directions, and this will be captured also by the receivers. Uh, in addition to cosmic, or as a part of cosmic background noise, the noise from stars, like the sun, for example. And effectively, the effect of the sun in some systems like radar systems and satellite communication system is critical. So when we are calculating the power budget for a receiver for satellite communication or a radar system, we should include the noise from the sun specifically. Lightning. Lightning also is a very important parameter for external noise. Gas discharge lamps. Any lamps surrounding you, and this lamps is based on gas discharge. This gas discharge is actually introducing some sort of ionized gas, and this ionized gas will introduce external noise. Uh, Radio and TV and cellular stations, for their purposes, they are not noise, but out of their purposes, they will be noise. For example, the TV signal is a noise for the cellular station, and the cellular station is an external noise for the TV receiver. So, when I'm using the TV, I'm intending to receive the TV signal. But the cellular stations will introduce some sort of external noise which can be captured by the TV receiver. So effectively, our transmitter systems represent some sort of external noise. In addition, wireless devices like mobile phone, wireless LAN, and so on, all these devices are transmitting and receiving signals. So uh, if I am not the receiver for a certain transmitter, this transmitter will represent a noise for me. So any wireless device represents some sort of external noise sources. Microwave ovens. Effectively, microwave oven is an example for electromagnetic coupling. In microwave oven, the microwave oven is not designed to radiate electromagnetic waves, but actually it radiates some electromagnetic waves. And these radiated electromagnetic waves will introduce some noise on the microwave receivers or RF receivers surrounding the microwave oven. In addition, in some cases like radar systems and some communication systems, uh, there are jamming devices which are sending high power signal to jam or to make the receivers of the other devices are unable to detect the required signal. So in the jamming system, it is intended by someone to transmit high power, and this high power is jamming the required signal for our receivers. So these other sort of external noise. Uh, in general, we are going to define something called white noise. White noise is defined as a white color. White color is composed of different wavelengths, and all these wavelengths nearly have the same intensity. In a similar way, if we are talking about a microwave signal noise, such that its intensity is nearly constant at all frequencies in the RF band or microwave band, so we are going to call this noise is white noise, such that it includes all the frequencies with the same intensity. So noise with a flat frequency spectrum is called as a white noise, and usually, for example, thermal noise is a white noise. And most types of noise are white noise, but some external noises are some external noise sources are not white noise. For example, if I'm talking about the TV transmitter or cellular communication transmitter, they are not white noise source because effectively they are specified at a certain frequencies. Uh, Similar case for jamming, for example, in jamming, maybe jamming is not a white noise because it is specified at a certain frequency. I'm jamming on a certain receiver at a certain frequency. So this is not a white noise. So the definition of the white noise is a noise with a flat frequency spectrum. And usually thermal noise is a flat noise or a white noise. And the white noise is usually uh, related to the thermal noise. So in the case of thermal noise, the thermal noise is proportional to the temperature or the effective temperature of the device. So usually in the case of white noise, we represent the white noise in terms of the equivalent noise temperature, even if it is not thermal noise. So the characterization of noise effect in RF microwave systems in terms of noise temperature or noise figure, and we will see that there's a relation between the noise figure and noise temperature, will apply to all types of noise regardless of the source, as long as the spectrum of the noise is relatively flat, or as long as this noise it can be considered as a white noise. So, for example, the cosmic noise, for example, the noise from the suns and stars, the thermal noise, all these types of noise can be represented as white noise, and this white noise can be represented in terms of noise temperature and noise figure. This is generally what is meant by white noise. We are going to discuss the thermal noise in details because, as I mentioned, white noise it can be represented in terms of thermal or equivalent temperature noise. So we are going to talk specifically on thermal noise bar, and we are starting with the thermal noise bar in a simple resistor. Assume that I have a resistor here, and this resistor has a temperature T, and the temperature here is the absolute temperature in Kelvin. So according to the thermal activity of the electrons and holes inside the resistor, there will be random motion of the charge carriers inside the resistor. This random motion will introduce random current, and this random current multiplied by the resistor will introduce random potential difference at the terminals of the resistor. Effectively, this random motion of the carrier has an average value equal 0. So we don't have a DC output from this resistor. So the average value of the output voltage is 0. However, the root mean square value of this voltage is not 0. And this root mean square value represents the thermal noise in the RF or the microwave signal. So we say that consider a resistor at a physical temperature T. This is the physical temperature of the resistor, and T here in degrees in Kelvin, which is the absolute temperature, not the temperature in Celsius. The electrons in the resistors are in random motion due to the temperature, with kinetic energy which is proportional to the temperature. This random motion produces more random current, and this more random current produces more random voltage fluctuations. So it will produce small random voltage fluctuation at the resistor terminals. This voltage has 0 average value, so we don't have a DC, but non-zero root mean square value. So effectively, the root mean square value represents the power. So we still have some power from these two terminals. The root mean square voltage of this thermal resistor is determined by Planck's black body radiation law. And we know that according to Planck's black body, the radiated power from black body is proportional to the temperature, and this radiation is proportional to the radiated frequency, such that the radiated energy equals the Planck's constant multiplied by the frequency. So according to the distribution of the power for the radiated power of black body, we can say that, okay, the radiated power here equals 4h. H here is a Planck's constant multiplied by the frequency, which is any frequency, over E to the power h multiplied by f over kt, where k is Boltzmann constant and T is the absolute temperature, minus 1. This is actually the Boltzmann power distribution multiplied by the operating bandwidth P. This is actually equal the RF or the root mean square power from the resistor, which is V squared over R. From this we can say that, okay, the output voltage, the root mean square voltage at the terminal of this resistor at the temperature T, it can be determined by this law. From this we can obtain the value of the thermal noise voltage. So this is actually the thermal voltage introduced inside the circuit which contains this resistor. So if I have a circuit which consists of only one resistor, we have such random voltage output from this circuit. And this represents actually the noise output from this circuit. And this noise has a frequency spectrum flat. So this is actually white noise, and it is constant at all frequencies. So the value of the noise at a certain bandwidth is determined by the value of these bandwidths. So the amplitude of the voltage, the noise voltage, equals the square root of 4 HF BR over e to the power HF over KT minus 1, where H here is the Planck's constant, which is 6.625 multiplied by 10 to the power minus 34 joule second, and K is Boltzmann constant, which is 1.38 multiplied by 10 to the power minus 23 joule per Kelvin, and T is the absolute temperature in Kelvin. B is the operating bandwidth in hertz, and it should be noted that the bandwidth here in hertz directly. F is the frequency in hertz, the center frequency of the bandwidth in hertz, and R is the value of the resistance in ohms. For microwave signals, assume that the frequency, let us assume that the maximum frequency which we are interested in is around 100 gigahertz. And assume that the temperature of this resistor is only 100 Kelvin. And actually 100 Kelvin is a very cold, because effectively 0 Kelvin is 200, 0 Celsius degrees is 273 Kelvin. So 100 Kelvin is a very low temperature. I remember liquid nitrogen is 77 Kelvin. So 100 Kelvin is a low temperature. So assume that just the temperature is 100 Kelvin and the frequency is 100 gigahertz. If we calculate the value of HF for 100 gigahertz, we find that HF is around 6.6 multiplied by 10 to the power minus 23. On the other hand, the value of KT at temperature only 100 Kelvin is 1.4 multiplied by 10 to the power minus 21. This means that the value of HF for the highest frequency I'm expecting in microwave, but actually nowadays we are talking about 300 gigahertz, but at least for 300 gigahertz, the value of HF is greater than the value of KT by order of 2. This means that this value is nearly 100 times of this value. So approximately we can say that, the value of KT is greater than HF by order of 2. The value of KT is greater than the value of H by order of 2. So KT is greater than HF by 100 times nearly. So usually we say that the value of HF is much smaller than the value of KT. In this case, the exponential term e to the power HF over KT, T here it should be capital T because this is temperature, so e to the power HF over KT, it can be approximated, assuming that HF is much smaller than KT, it can be approximated e to the power HF over KT minus 1 can be approximated as HF over KT. So we can replace the denominator here by HF over KT, And from this HF will be eliminated with this HF. This means that the noise voltage at the resistor terminal, it will be approximately as square root 4 multiplied by Boltzmann constant K multiplied by the absolute temperature T multiplied by the operating bandwidth B in Hertz multiplied by the value of the resistance in Ohm. And this is known as the relay-Jaynes approximation. And it should be noted that this approximation is valid only if the value of HF is much smaller than KT. If the frequency is very high, such that the value of HF is not much smaller than KT, or if the temperature is very small, this relation it would be not valid. So this relation is valid only for small frequency and high temperature. This equation is valid only for small frequency, smaller than 100 gigahertz, and high temperature is greater than 100 Kelvin. So this relay-Jaynes approximation for the noise voltage from a resistor due to thermal noise. This is a very simple approximation for the definition of the noise voltage from a resistor. The question now, what will be the situation if we have a complete microwave circuit? What will be the power of a microwave circuit with a noisy resistor? This is actually what we are going to talk about in the following video, the equivalent circuit for a noisy resistor. And from this equivalent circuit, we are going to discuss what is the effect of the noise resistor on microwave and RF microwave circuits. Okay, all right.